Custom node-based IK solver. So the current IK setup uses the IK solver of Maya and the joints to get the positions of the IK. But the IK solver of Maya is an iterative solver because it is also capable of solving bone chains with more than two joints. So it's taking multiple iterations to change the rotations to get the last joint or the end effector, which is, if you look at the joint, the second to last joint has an end effector which has the same translation as the last joint, so it will always be in the same position of the last joint. So Maya is changing all the rotations of the joints to get them to align within the plane set with the pole vector to get the end effector to the position of the IK handle. And it takes multiple steps, and it uses joints, and joints have extra matrix multiplications inside of them because of the joint orient matrix that is calculated as well, and the inverse scale matrix that is calculated because of the plug of the scale of the parent going into the inverse scale of the child joint, and this calculates an inverse world matrix to prevent the children from scaling with the parent. So all these take up extra calculations. So we could also, because this is a simple triangle, it has three sides, and we can solve this with trigonometry and math nodes. So let's look at how we would solve this with Maya native nodes without the Maya IK solver to save some performance cycles and speed up the rig. So if we look at the rig in 3D, we can see that this is a triangle with nice straight lines, as you can see, where you have the sides A, B, and C, and the opposite angles of the sides are angles capital A and capital C and capital B. These are the angles, and if you want to get the angle of B, for example, you can use the law of cosines, which says the cosine of angle B, right, equals A squared plus C squared minus B squared divided by 2AC. So this equation will give you the cosine of angle B. So if we take the result of this and take the arc cosine of this result, we will get the angle of B, and we can use that to set the angle of the IK solver. So if you imagine that in the default state of the bone, so to speak, it would be pointing straight to the end. Then you can rotate it by B to get to this rotation angle. So let's look at how we could set this up in the Maya node editor. So let's open up a new tab. So we need the A, B, and C, which are the sides of the triangle. We know because this is the length of the upper arm, this is the length of the lower arm, and this is the length between the start and the end of the arm. So let's get these nodes. We have them right here. The arm length is C, and the upper arm initial length is A and B, but we already set up the IK stretching, so we can just as well use the scaled upper and lower length because they only scale when the arm is actually longer than the breast length. So we take the arm length and the upper and lower length. We add them to the graph. So this is A, this is B, and this is C. So let's square them first. So we can just simply create a multiply node and take the output and put it in twice. That's the same as squaring it. Let's call this, for now, to make it clear, a squared. And duplicate this. And call this b squared. Like this. And then we can duplicate this and call it c squared. So now we have this set up, and then we can make the upper part the numerator of the equation. So let's say we take a sum, and we say a squared plus c squared, and then we do a subtract mode, and we say this minus b squared, and then we need to make the denominator. So this is another multiply node. For that we need a static value of 2, so I'm not sure if this node, if you break the connection, it gets removed as well. So let's just try that for now. If we now remove this connection, no, it gets removed as well. By the way, you can, if you press Shift Alt, you can click and drag and cut lines. So that's nice to have sometimes. So no, we cannot, without coding, add a static value. So let's make a float constant again. Set it, nope, not a float condition, a float constant. Set its value to 2. And take the output, plug it into the first plug, and then A and C. So the upper is A, and the arm length is C. And now we have to divide it. So we divide the upper part by the denominator. And then we have the result of this equation. So if we now take the inverse of the cosine, so this gets you the cosine of the angle. If you want the angle from the cosine value, you use the arc cosine, which is the a cos function in Maya. So now we can plug this in, and the output now is an angle. So, all right. And let's, for now, keep the joints. Just remove the IK handle and drive them to see how it works. So let's remove the IK handle. And where did my joints go? Ah, there. Okay. We can keep the connections to the TX, because that's driving the length. We'll just set the rotation to 0 for now. And the input of the joint is now still the upper arm FK, which is pointing in this direction. We don't want that for now, so let's cut this connection and reset its parent offset, so we can just put 0 values. So now it is on the world orientation plane, but for now we keep it there so we can see the trigonometry, and then if we have fixed the trigonometry, we can position it at the correct place in space. Okay, so we now take these joints, add them to the graph here. The whole point was to remove the joints, but for visual explanation it's nice to have them. Afterwards we will remove them. So the upper joint, we can see it's we want to rotate it around the y-axis. So we're going to, because it is aligned in the arm, the x-axis is the forward direction and the y-axis is the direction that points into the direction of the elbow, which is the direction we want to bend in. So we have to rotate it negative 90 degree in the x direction. So we'll set the offset parent matrix of the joint to have the rotation for now. So you can see that it is aligned in the flat, or I say in the xz plane now. So if we rotate the z, this is what we want to have happening. So if we now take the output of the arc cosine and we plug it into the rotate z of the joint, you will see that the rotation, well, matches the triangle that we drew. Not completely, because we're changing the view, but the angle is correct. So now we have to set the angle on the lower joint, which is solving for c, which is the same equation, more or less, just swapping around the b's and c's. So the cosine of c equals, and then we have a squared plus b squared minus c squared divided by 2 and then ab. So we can create this as well in the same way. So we start by creating a sum node, and then we add the a squared and b squared. So a squared and b squared, and then we subtract the c squared from it. So we plug this in here, we take the c squared, so this is the numerator, and then we make the denominator. So again we create a multiply node, and then we reuse the float 2 value, and then we add the a and the b, so the upper and the lower, and then we divide them. So we take the numerator and then the denominator, and then we have the result of the equation. So now again we can use the a cosine, the arc cosine, to get the angle, and we also here we would use the rotate around the z-axis. But now if we plug this in into the rotate z, you will see that it rotates in the wrong direction. But you have to think about, if the arm would be straight, these two axes a and b, edges, would lie flat on the c. So c would be the same as a and b appended, and then the angle of c is 180 degrees. But for us to get a straight joint chain, we have to have a rotation of 0. So we have to subtract the angle of 180. Because if, for example, AB were the same size and C would be 0, then A and B would form an angle of 180 degrees in the Maya logic. But in the triangle logic, then C would be 0. So subtracting the angle from 180 will give us the correct angle. So if we do subtract, and then we set this to 180, and then we plug in the angle, and then we use this to drive the rotate z. We still get the wrong direction, and this is because we have to negate the angle as well. So after subtracting, we have to also negate, because the angle will always be positive, the angle we get from this triangle. And if you look at the z-axis, if you think about the right-handed rule or the arcing fingers when you make a thumbs up sign, the positive rotation is counterclockwise, and we want to, in this case, rotate clockwise. So we have to negate the angle. So we take the angle, put it in the negate, and then the output of this we plug in the rotate z. And now we can see that the solve is correct. if we now move the IK handle, you can see that the IK solver nicely solves for the angles. So this is the bone rotation part. So now we have to do the alignment of the initial joint, because now it's at the root in world space, and we need it to be at the position of the actual arm. So let me clear the paint view. So now we have to multiply the matrix of this joint with the matrix that gets us to the arm position. And what we know is that now it's oriented in world space, so the x-axis is actually the axis where the end joint slides over. So the x-axis is basically what we need to have from the arm upper control to the hand IK control. So that is the x-axis. And the negative z-axis, in this case, will be the axis that is created by the elbow control. So we need to create an aim matrix that aims from the upper arm position to the hand position with the x-axis, and the negative z-axis is aligned with the elbow control. So let's create the aim matrix. And for the upper arm, we will use the same matrix. Let's see if that we used for the upper arm control, because this one is moving along with the main control, and that's what we want. So we take this node, add it here, and we take that and put it into the input matrix. And then we take the hand control, IK hand control, and we take the world matrix plug and plug it into the primary target matrix. And then we say we want the x-axis to aim at this position, so that's correct. And now we take the control, the elbow control. This is a leftover from the IK, we can just remove that one. We take this control, we add it, and we plug its world matrix into the secondary target matrix. And then we say, okay, alignment-wise, the positive y direction of this control is the vector we're going to use. So we're going to align with the positive y direction, and we wanted to align the negative z axis. So 0, -1. So now we have created, if we create a temporary locator, we can see that if we plug it into the offset parent matrix, we have created the matrix that points with the x-axis to the IK hand control, and with the negative z-axis aligned with the pull factor control, or the elbow control. So what we can do now is take the aim matrix output and plug it into the world matrix of the parent offset matrix of the upper IK control. And I think we're going to get an offset, but let's look. Yes, because we already had the offset parent matrix set to 90-degree rotation around the x-axis, so we could visualize it. So we have to not align the, let's see, not the z-axis, but as well the, let's see, y-axis. Yeah, so we need the y-axis in the end after all. So now it's nicely aligned. And now we have a functioning IK solver without using the Maya IK solver, we're just using trigonometry nodes. And it still has the stretch because we already set that up when we use the Maya IK solver. So now we have a very quick and Maya node-based IK solver with stretch. It is more nodes than one IK solver, but I tested it in another file and it's actually faster, even though it has more nodes, and the node overhead does not amount to more than the extra calculations done in the IK solver when iterating over the solver steps. So it is quicker still. But the whole point was to get rid of the joints, and we still have the joints in the setup. So let's replace the joints with temporary locators, so we can use them when using or blending the FK and IK to the actual joints we're going to use for skinning. So for this, we can recreate this matrix by multiplying the local matrix that's using the angle to build a matrix, and that's multiplied with the offset parent matrix. We can recreate it in a mult matrix node. So if we do mult matrix, and then we take the or create a compose matrix. Caps lock is on apparently. Compose matrix. And we take the output rotation and put it into the rotate Z. And we take the output into the first plug of the matrix, mult matrix node, and we take the offset parent matrix coming from the aim matrix and plug it into the second part. We now, if we create a locator, and we plug this into the offset parent matrix, we have the locator that is at the position of this joint. So let's call this arm left upper IK temp, because we're not going to use it, but just for now, for visual cues, we can use it. And we'll call this the IK, nope. IK world matrix. But there's still something we can do to optimize this, because in the compose matrix node, apart from the fact that it's creating a translate matrix, a scale matrix, a shear matrix, and a rotation matrix, or 3 rotation matrix, if you recall the matrix video I made, one for the X, one for the Y, one for the Z, so it's 3 matrices. And each matrix uses a cosine and a sine calculation. So it's actually quite a lot of calculations for just creating a matrix that has the one rotation in it. So we can also recreate this using 3 nodes or 4 nodes, but with a lot less calculations. So if we create a 4x4 matrix, we can create a matrix by directly setting the values of the matrix. So this is the 1 0 to, sorry, the 0 0 to 0 3 is the basis vector x, and this is the basis vector y, z, and the translation vector. And if you remember correctly, we can use the cosine and sine of the angle that we created to drive the 4x4 matrix basis vector values. So if we take the cosine of the angle, and we also make a sine, we plug the angle into the sine, then show all the inputs of the 4x4 matrix. So because we are rotating around the z-axis, the z-axis itself does not change. So the z-axis, so these values do not change, and we're not going to set a translation, so these values do not change as well. So we're only rotating the x vector and the y basis vector. So with a rotation of 0, the cosine amounts to 1. So for the x-axis, we want to have the cosine in the 0, 0 position, and the sine in the 0, 1 position, and as well the z component does not change because we are rotating around the z-axis. And then for the y basis vector. The cosine, which solves to 1 with an angle of 0, we should plug that into the value that has the 1, so the 1, 1, the y component of the y basis vector. And then, remembering the matrix video, we have to negate the sine value. So negating, we have to plug the output, not the angle. Sorry. So now it's set up correctly. So we have to negate the output and then plug that into the x component of the y basis vector. So now we have set up the rotation matrix. So now I hear you thinking, hold on a minute, you're calculating the cosine from an arc cosine, which basically converts the value back and forth. So instead of using the cosine, we can just as well connect the value directly into the matrix by skipping the cosine value. So if these nodes cancel each other out, so taking the output before it goes into arc cosine and plug that into the slot that has the arc cosine connection, we can just completely discard the cosine, and now we have 3 nodes that creates the same matrix as the composed matrix, with a lot less math behind the scenes. So if we look at them and compare them, you can see that if you look at the matrix, you'll see it only has a 46-degree rotation around the z-axis, and if you take the output of this matrix and connect it, you'll see the same rotation. So we have recreated the rotation matrix, but only the rotate z matrix. So instead of creating 1, 2, 3, 4, 5, 6 matrices for multiplication, we just created 1. So we can remove that one, and we can rename these to, let's call this one the upper IK local rod matrix, and this the upper IK sine, this one sine negated, this one the upper IK arc cosine, and I'll just rename these nodes off screen, so you won't have to look at me typing node names. Okay, so I've nicely renamed everything, so it's more logical. And now we have to do the same for the lower joint. So we have created a locator that's at the position of the upper joint. So now we have to create the same thing for the lower joint. So again, we're going to make a sine node and a 4x4 matrix and a negate node, and we're going to plug the output of the angle into the sine node, and then the output of the sine node into the negate node, and then the 4x4 matrix node. We can do the same. So we take the cosine value, which is all the way back here, because this is the 180 angle correction and the negating of the angle. So we take the cosine value, plug it into the x component of the basis vector x, and we take the cosine value and plug it into the y component of the basis vector y. We take the sine value, put it in the y component of the basis vector x, and then we take the negated sine value and plug it into the x value of the basis component y, basis vector y. So now we have the local rotation matrix, or sorts of, because if we now have the pure rotation matrix, and if we want to create the matrix that is, let's say, the offset matrix relative to this matrix, we have to also set the translation with the length of the upper arm. So if, for example, I would create now the not matrix node and plug in the matrix, the rotation matrix we created, and then take the world matrix of the locator, which is its parent, plug it into the second plug, and if we now create another locator, and we take the matrix sum and put it in the offset parent matrix, you will see that the orientation is correct, but it's at the wrong position. So what we have to do now is also take the upper length, so the scaled length of the upper arm, and plug it into the translate x component of the matrix. And now if we look, we have the correct position. And I see I have made an error here because the rotation is not correct. So let's see what happened. Yes, of course, I was nicely telling you about how I negated the angle and subtracted it from 180. So of course, this is not the same cosine value as would come from taking the cosine of this angle. But we can fix this by negating the cosine here. So if we create another negate value and plug it in, and then we swap the connections with the negated values, we now have the locator in the correct orientation. And if we run the local scale and we take the arm controller, we can see that now the rotation is correct. So now we have a locator that is the lower arm. If we multiply its local matrix with the parent matrix, we get its world matrix, and we still have the local matrix because we're going to use the local matrix for blending between IK and FK. So it's nice to have this. So let's call this the, I call this upper IK world matrix. And we'll call this the local matrix, and this the world matrix, but it should be lower, and here as well. And this is the lower IK temp locator. Whatever. Okay, so now we have this, and then one thing rests is that's creating the hand position, and for that we need to use the for the world matrix we can just use the IK controller, but only if stretching is enabled. If we create a switch where we can disable and enable stretch in the rig, we cannot use the world matrix of the hand control, because then it would be, well, disconnected from the arm itself. So let's make that switch first and then create the hand local matrix of the IK. So on the arm setup, create another attribute, and let's say enable stretch, or IK stretch to be more precise, and we can make it a float, but is that useful? I don't know, maybe you want to blend somewhere in animation, so let's make it a float from ranging from 1 to 0 with the default being off, I guess. Doesn't really matter for now. Okay, so we need to look at our, let's look at here, where we set up the stretching. So here we have the upper arm length and the lower arm length being stretched with the arm scalar. And now we need to blend this value from this value to 1 if we want to disable the scaling, because if we want to disable the stretching, the output of this should always be 1. So we can do that with a remap value. And we can take the settings node, it's right here. We can take the enable IK stretch and put it into the input value. And then we can shrink this again. And then the input value goes from 0 to 1. And when it's 0, you want the stretching to be disabled, so the output should be 1. And if the input value is 1, we want to enable the stretching, so the output should be, so the input is 1, so it's the max, so the output value should be the stretch scalar value. So the output max should be this value. So now it's, because it's not stretched, they are both 1. And if we now take the out value and plug it in here, and if we now put the arm in a stretch position, you will see that it's not stretching anymore. And if we go to the setup and we enable the stretch, you can see that it's gradually fading into the stretched position. So for now I have docked this under the settings node. This is not something that an animator would be exposed to. So if you want to have the animator be able to set the stretching to on or off, or some value in between, we have to relocate the stretch value to a control, for example on the IK control itself. But for now we'll leave it as a statically set value on the rig, unexposed to the animator. So let's rename this to left arm enable IK stretch. Okay, now that's out of the way. We can look at the IK hand position, because now when stretching is off, for example, if the IK control is here, we cannot use the worldspace location because we need to be at this position with this orientation. So we should get the world matrix of the IK hand control as a relative matrix to the arm lower IK. So this is the arm lower IK, or is it? It is still stretching. Yes, it's actually good that this happened because I made an error. You can see that if I stretch the arm, although the joints do not stretch, the locator, however, does stretch. And if you look at the matrix of this node, you can see that it has scale values as well. And the upper arm has scale values too. And this is because the upper and lower length have nicely been locked, but the arm length is still the length that is going from the arm position to the hand position. So this is used in the calculation, which gives values larger than, it gives basis vectors with a length larger than 1, as you can see. So that's why scaling is introduced. So we do not want that. We do not want the C edge of the triangle. If you remember, then the upper is the A, the lower is the B, and the one connecting the end point and the shoulder is edge C. but now that she is going from the upper all the way to the hand, which is longer, which is a broken triangle, and then of course the trigonometry for solving triangles breaks. So what we have to do is we have to limit the length that we're using for the trigonometry of the arm to the maximum length of the upper and lower arm. So that's, if we have the upper and lower arm scaled, we have those here. So what we can do another add node or sum node. So we get the maximum length of the scaled arms. We already have a sum of the initial length, but we need to use the sum of the scaled lengths, because now we introduced a scalable enabler for the length scale, which also slowly scales in the length of the upper and lower, and that's what we have to use for solving the triangle. So we need another sum, and we'll call this arm length. Let's call this one current length to not confuse it, and this arm not upper but length. And so now we have the length that is the maximum length of the C edge of the triangle. So now we can take a min, because we always want the shortest edge, because if it's longer we want to use the maximum length of the upper and lower arm combined, and if it's shorter then we want the shorter value. So we take the min value of these two, and then we use this output to drive the triangle solver. And now you can see that the locator nicely holds at the position of the lower arm. So we'll call this lower arm clamped length. Alright, so now we're back and we have an actual locator with no scale and at the correct position. So now we can take the arm, the IK worldspace matrix, and convert it to a relative matrix relative to this locator. So this one I don't need here. We can make the mult matrix node, and we can take the world matrix of the hand IK control, plug it into the first slot, and then we want to use the inverser world matrix of this lower arm position, but we're not going to use this locator, it's just a temporary one. So we're going to use an inverser matrix node to calculate the inverser matrix of the world matrix of the lower arm IK. So this is lower arm world inverser matrix, and we take this and plug it into the second slot, and now we have the hand local matrix. So it's basically the equivalent of this matrix, but then for the lower, the hand. So we say hand IK local matrix. Oops. So if we now take another mult matrix node and we multiply the output of this with the output of the lower arm IK, and we create another locator, we will see that this is at the position of the hand. Okay, but now still it's detached from the arm because it has the correct orientation, but the position is wrong. The position should be at the end of the arm. So what we can do is, in this local matrix, we have the translation set that is from this position to here. So we have to replace the length with the length of the lower arm. And we can do this in two ways. We can use a pick matrix to isolate the basis vectors from the translation. So basically, if you plug the local matrix into the pick matrix, the rotate, shear, and scale, they are all calculated or encapsulated in the basis vectors x, y, and z of the matrix. So the first three rows. The translation is the fourth row. So if we disable translate, Maya discards the fourth row, and then the result is the matrix that only has the scale, rotate, and shear. And then we can multiply this with a matrix that only has the translation, and then we can set the translation, so to speak. But this involves another mult matrix node as well. Matrices are multiplied, and you just want to set the values. So we can just do this for now. Oh, not that one. To show you. Like this. So if we now have this matrix that does not have the translation, so if we output this into the mult matrix node, and then for now just plug it in, you'll see that the locator is now positioned at the position of its parent, namely the lower arm, but has the right orientation. So if I now rotate the hand control, you can see that the rotation matches. But now we have to set the translation, and to get a translation matrix, you can either use a compose matrix, but then again that uses or calculates rotation matrix and scale matrices as well, or has an if clause that could cause some delay in the calculations. So we could just basically make a 4x4 matrix to create the translation matrix. It's faster. We can just take the length of the lower arm and plug it directly. Oh, I lost my plug. The length of the lower arm, and plug it directly into the x component of the translation vector. And then I can use this to multiply the other matrix with. And now we have the locator at the correct position. So now if I move it, the locator will snap to the position when the arm is shorter than its max length, and if its max length is reached, it will just stay at this position. But for this we are dissecting a matrix and multiplying two matrices to get this matrix. There is another way. We can use we need a 4x4 matrix because we're going to create the matrix, and then we can use, it takes more nodes, but it should be less calculations, a row from matrix. And it's a shame that Maya does not have a node where you can just expose all values of the matrix. I made a node myself in C++, but I will not use it because you don't have it, and it is fairly easy, but it's a shame that Maya does not supply a node where you can just plug in a matrix and then access all of its values of the matrix, all 16 values, because that would save nodes and it's super useful. But unfortunately, we have to just do it this way. If we set this row for matrix to 0, we just basically get the basis vector x. So we can take the output of this and plug it into the basis vector x plugs, and then we can duplicate it and plug the same matrix in, which is the rotation local matrix that gets us from the lower arm position to the hand IK control position. And we take the outputs of this one, plug it into the y basis vector plugs, and of course we have to set this to the second row, and then we take another node and plug in the matrix and set it to the second row, the second input, so the third row, which is the basis vector z, and we plug it in the basis vector z values. So now basically we have created a matrix which has the same, well, it basically is the same as the pick matrix, because we have removed the translation. We have plugged all the basis vectors in without modifying them. If you use scale, rotate, and shear checked in the pick matrix, I think, because I don't know what happens inside the node exactly, Maya will check if all of these are checked. It will just directly port the basis vectors into the output matrix and discard the translation. If you uncheck share, it will perform cross products to realign the vectors to make them orthogonal to one another. If you uncheck scale, it will normalize the basis vectors. And if you uncheck rotate, it will just take the, depending on if you have share or scale unchecked or checked, it will take the length of the vector and multiply it with the basis vector x as it is not rotated, and apply the shear as well to this vector. So depending on what you have checked and unchecked, less or more math happens within the pick matrix node. So in this case, I like this setup better. It takes a little bit more nodes, but I think in the end it's still quicker, because now we can directly take the translation as well, the lower length, and plug it into the translate x, and now we have created this. So it takes one node more, but it is less calculation, because this is basically just this node is basically just or internally setting the values from the matrix, so it does not do any math at all. And we can take now this output and plug it into the first plug, and we have the same output. So I prefer this option, but yeah, so it's a preference because it's slightly quicker. Then for naming, let's call this x is x, and this x is y, and this one x is z, and this is then the and ik local matrix. So let's call this base local matrix, for lack of a better word for now. Okay, so now we have the local matrix of the hand as well, and we have constructed the world matrix as well. And this is going to be the temporary locator. So let's see if everything is nicely named. Oh, we're missing some names here still. So let me set those quickly. So those are renamed now as well nicely. And then we have our IK added to the rig. We can discard the joins because we're not using that anymore. And we have everything done in the node editor. This one can be deleted. We'll leave the temporary locators outside of the module because we're not using them, we're just temporary locators. Let's reset our controls to their positions, main control. Okay, so now we're back to the beginning, and we still have our capability to change the rig with everything following nicely along. Changing the guides will rearrange the FK and IK controllers, and the rig stays interactive. It can still be used as expected. Okay, as a last detail, I renamed the aim constraint to be the arm base world matrix. node, so that it is clear what it does. The rest of the nodes were nicely named already. And now we have a functioning IK control rig.